Hello, everyone. Thank you for joining us today for this webinar. We've got two amazing speakers talking about reverse osmosis. We're going to focus on enhancing efficiency and fouling control. Today, I'm lucky to be joined by Beatriz Colacioppo from the US and Jochen Kallenberg from Switzerland. Thank you both for joining us for this session of the Water Academy technical courses. And first, we're going to start with Jochen, and we're going to be talking about the technology and how it helps in terms of reducing fouling. Jochen, the floor is yours.
Thank you, Walid. Thank you, everybody, for joining the webinar. I will assume that everybody is seeing my presentation, and I will start on the topic of how do we help to improve the efficiency and avoid or reduce fouling in reverse osmosis systems. So we are helping here with our activated filter media. That's a filter media you can use in conventional sand filters for existing and to upgrade new systems. So the AFM activated filter media is used in different business areas. We are having three different ones. One is public and private pools, life support systems like aquaria and aquaculture, and then of course water treatment. That's what we are talking about today. We as a company are located in different places around the world. We have two factories. One is located in Scotland, and one is in Switzerland. The one in Switzerland is a new one built in 2020. Scotland actually is older, but it has been upgraded several times. The biggest build up was made in 2013. We have companies and offices in Germany, US, and China. And we usually work through a global distribution chain with different distributors in different countries. Just jumping into how is the product produced, just that you a little bit understand as a background where the filter media comes from. So we are using green and brown soda lime silica glass. In the first step, we are separating the glass and only using the green and the brown glass. One of the reasons is because we want to use the chromium oxide and the ferric oxide, which we use in our activation process, or which we use also in the function of the media, which I will explain later on. So then in the next step, brushing and sieving, we produce different types and grades of our filter media. We have 5 different grades from supporting layers up to 5 standard and fine filtration layer media. So after the crushing and sieving, we have a specific so-called activation process. That's actually why the product is called activated filter media, because we modify the surface area in this process, which is consisting of a 3-step chemical and thermal process. We modify it chemically, and then we fuse that into the surface with a high heat. At the end, we, of course, have our quality control to make sure that the product is always consistent in how we produce it. That's actually also a difference to other filter media, because we are producing it in 2 different locations with the same production way of producing it, so to say, so that we can provide consistently the same quality and performance from any of our factories, which is actually different to sand. Sand is mined or kind of taken out from riverbeds with dredging and then sieved at different locations in the world. And that actually leads to quite different performance of the sand wherever you are in the world. So this is different with our media. You have it designed once and you can use the performance wherever you are. So as I mentioned, 2 factories, together 55,000 tons we are producing. So the Swiss factory is slightly larger than the Scottish factory, but both are in the same high-end manufacturing. These are both fully automated, so we only need 3 people to run it, even if it's quite a big factory. Everything is fully automated, even with AI controlled. That's a picture on the Swiss factory. We are using actually also electricity from the roof and the facades, where we use photovoltaic, which is then stored into large batteries. Just before we go through the product itself and the benefits in the reverse osmosis treatment, just to mention that the product has different certifications for drinking water approvals. All of the quality management systems are in place. We also sell to food and beverage companies like Coca-Cola, Pepsi, and so on. That's why we have the so-called HACCP approval, using it in the food and beverage industry. We also have just recently get the approval from a new EN norm, which is published last December, which is used for glass beads and granulates for use in treatment of water intended for human consumption. So it's also in Europe a specific new norm on the glass media to use for drinking water treatment. So what's the difference to other filter media, or let's say compare it to sand? So first of all, as I mentioned, we are modifying the surface area. By this modification, we can provide kind of a biofouling protection. This happens through the metal oxides in the glass, which are fused in the manufacturing of the glass itself. With our modification, we increase the surface area, but also provide bioresistance on the surface, which means we are not killing bacteria, we are not disinfecting the water. We just generate a very small amount of hydroxy radicals, which are then avoiding that bacteria want to attach to the surface. So this actually provides for the biofouling resistance, which is important because the surface area in a sand filter, like in a membrane reverse osmosis plant, the surface area is quite big with all the membranes. Upstream the RO, the biggest surface area of contact with the water coming in is the media filter. Here we are providing protection on biofouling growth, which is one of the first key requirements if you want to treat the water before reverse osmosis. Secondly, benefiting the first property, we increase the surface area during this activation process. Actually, this helps vice versa, because increasing the surface area, we can actually provide enough of the hydroxy radicals to protect the surface from bacteria wanting to attach and grow a biofilm. We are not disinfecting the water, we are not killing bacteria, we just avoid that bacteria attach to the surface and grow the biofilm. So that's the one's main properties of any of our product types. Then we have two different types, AFM-NG for new generation and AFM-S for standard. These have been developed for different purposes other than standard filtration, performance, and being bioresistant. These two differences make a difference in where you may use one or the other product. The standard is used for heavy metal removal, is better for heavy metal removal, removes down particles to 4 microns, up to a 97% removal efficiency. The hydrophilic is the AFM standard, it's negative charged. The hydrophobic version is neutral charged, but it can remove quite efficiently oil and hydrocarbons, and as well microplastics, down to particles of 1 micron, up to 95% removal efficiency. So here you can see water is soaking easily into the AFM standard, like with any filter media. If you drop water on top of our AFM, you can see the water is repelling from the surface area. That's how you can see hydrophobicity on the surface. What are the benefits here if you go now to the different properties in media filtration or on any surface where water comes in contact with? You have bacteria sticking to the surface. They generate the so-called EPS structure, which is mainly consisting, this is like the biofilm. You can touch it and feel it. It's like a slippery surface, mainly polysaccharides. So this is called extracellular polymeric substances. These lead to biofilm formation, and you want to control it by using chlorine as a disinfecting or as a killer of the bacteria to avoid the biological growth. And as many of you may already know, by using chlorine in a continuous dosing, bacteria can adapt, and actually you can have the regrowth of bacteria or biofilm, which may lead to even higher biofouling potential or growth in your membrane system. Yeah? So what happens in a sand filter? Bacteria grow, they build clumps, mothball formation, which actually then leads to channeling. And this channeling actually may provide for more bad water quality or more bacteria passing through the filter, as you may have in the feed of the filter. Yeah? This is actually one of the reasons why you need to disinfect sand filter regularly, because they grow bacteria and they lead to this channeling. Also, the backwash is very important to avoid the formation of channels. Yeah. Anyway, by using AFM, we have a big benefit here. We can avoid this clumping formation. The biofouling in general is reduced, and this leads to a much more reliable filtration performance. Because we have no biofilm or a much reduced biofilm formation, we stop the growth of pathogens, like Pseudomonas or Legionella, very famous ones, especially in warm areas where these grow. They use the EPS structure as a host to grow. If you have much less, you dramatically reduce your availability or the growth of pathogens. So with AFM, we can actually quite good remove or stop the growth. If you go down to the other property, let's say surface area, you're taking the same volume for sand and for AFM 5 cubic meters, for example. We have here 5 cubic meters, a surface area of 320,000 square meters versus 23,000 square meters for sand in a 5 cubic meters. So that actually shows you why the filter media AFM can remove much higher amount of very small particles here. So this is the performance graph. This is actually quite done independent by a French Institute for Filtration. This is not done from our side, this curve. As you can see here, that sand drops quite fast at 20 micron particle removal. We can see in many places in the world that the sand removal rate of 95% is actually much earlier, maybe already at 30 microns when it starts to drop in the performance of removing finer particles. You can see our AFM, the different grades reach 4 microns up to 1 micron removal up to 95%. That actually makes a big difference, especially in RO pretreatment, where you want to reduce the SDI or reduce the organic or inorganic fouling in your membranes by removing these fine particles to extend the runtime of your cartridge filter, not replacing them in the frequency you're doing it today. So here with our media, we dramatically reduce the exchange rate required for cartridge filters. If you look from a different perspective on the filtration graphs, like on the process for separation, you can see that sand is still in particular filtration area. It's on the bottom area, you see that, whereas AFM is already within microfiltration. If you would add here some coagulants, flocculants, you can actually achieve a high rate removal of very fine particles. We are not saying we are replacing UF membranes with our media. We just say we close the gap between conventional media filtration and ultrafiltration microfiltration. If you then go to the backwash, that's a key in media filtration. We have also a lot of savings here because our media is lighter than sand. So in the retrofit, the backwash performance is better because in the same system with the same backwash pump, our media is expanding better. Because we have less biofouling, we also reach a better performance in the removal of the impurities you have filtered before. This goes down up to savings of 50% of backwash water and also savings of a lot of energy. We also don't need air for backwash, which is typically required for many processes when sand is used for the media filtration process to detach whatever has been attached to the surface of the sand. Here you can see a typical backwash process. It starts at the beginning, then you see a big plume at 30 seconds coming out with the impurities. After 2 or 3 minutes, the water gets clear. And once it's clear, the backwash is finished. You typically want to achieve a backwash bed expansion of 15 to 20%, actually better 20%, because at 20% you fluidize the media bed and then you have a very good removal rate of your impurities from your filter. That's a typical curve for sand, which is highly polluted by organics. It leads to very inconsistent filtration. You can see the filtration in backwash is not very similar, and you have channeling, which you see between the red lines. There is no filtration because you have channeling. In the same system we changed it to our filter media, and you have a very consistent filtration, kind of similar graph you get for an ultrafiltration, infiltration, and backwash of your filter. Typical operating conditions for media filters, but we can actually run at higher filtration velocities. We can run up to 30 meters per hour filtration velocity. Backwash, we typically run at 30 to 50 meters per hour because we have a shorter backwash time, which saves water and energy. We are typically around 3 to 5 minutes, maybe 10 minutes is a little bit long. We have 5 minutes water only backwash. It's triggered at 500 millibars pressure increase after your last backwash. So you start your filtration after last backwash. If you reach 500 millibars, you start to backwash your filter. We have a comprehensive manual to operate our filter media with all instructions, how you operate it and how you can get the best out of our filter media. If you then go to use our media in RO pretreatment, there's a couple of benefits. So first of all, that's a standard process scheme, as probably everybody knows about it. You have chlorine dosing, which may be intermittent or none, but very often in many ways, very often in seawater plants, you have this intermittent chlorine dosing to disinfect your system up to the RO plant. Actually, mainly one of the key issues here are the media filter, to disinfect the sand. You need an air scouring blower, you need sodium metabisulfite, and you need a cartridge filter. That's all part of your pretreatment. That's a conventional way. If you use AFM, you have some key benefits. You can reduce the chlorine consumption because we need much less chlorine, or actually we wouldn't actually need any chlorine disinfection, yeah, because you remove down to very fine particles. Fine particles are removed without the need of coagulant or flocculant, or you add only a much smaller amount. So there is a savings also on the coagulant dosing. We very often don't require the air scouring. So air scouring means you save on capex, you save on opex, because you only need water for the backwash. And as mentioned before, cartridge filter exchange rate is reduced because we remove much finer particles. So if you go to an optimized system where we only use AFM and everything has been optimized with AFM, you can see that if there is no chlorine required, we reduce or almost no coagulant required, no air scouring, and no other than the downstream sodium metabisulfite, or much less. Yeah, cartridge filter lifetime is extended, so there's a lot of OPEX savings around using our filter media. Yeah? So even if our filter media is more expensive, the return on investment is often within a couple of years, 2, maybe 3 years, sometimes actually even on the first day. Depends on the issues you have in your RO plant. So as a summary, if you look on the RO pretreatment, there's a key benefits in biological fouling because we avoid the growth of bacteria. Then if you look on particulate or colloidal fouling, we remove particles down to 1 micron. That's much better than sand, which probably ends up at 20, 30 ppm and drops very fast with the removal of finer particles. Organics, again, same thing. We can remove it much more efficient than with sand or other filter media, natural filter medias. Of course, against scaling, we cannot do anything against scaling. Only kind of a benefit if you have less fouling on your RO membranes, also your salt scaling is reduced. For filter media before RO, there's a couple of benefits. We don't need the amount of chemicals because we just operate with water only, or maybe sometimes air may be required, but typically we don't need it. That our media is more robust or forgiving in different water quality conditions. So if you have water quality may change in the winter or summertime to high algae growth or high suspended solids. With UF, you start to have a very high frequency of backwash and cleaning cycles. Whereas with our filter media, this is more better controllable under a wide range of operating conditions. We have a lifetime of 20 years and we guarantee at least 10 years of operations. Also, if you look on coagulant flocculant types, we don't have any limitations on coagulant and flocculants to be used. We have a much lower life cycle cost, which is one of the key indicators for selecting your pretreatment. Yeah? We may have equal or lower capex. This typically depends slightly on the size of your reverse osmosis plant. Then we go to some case studies showing you what we have achieved for benefit in real-world applications. This was a project we did in Spain. This plant had issues with particulates. You can see that on the bottom left side. So particle range of particles coming to the media filter were actually 50 to 80, or let's say more than 50, 60% particles less than 10 microns. They passed the sand filter. As a consequence, they could only run the plant at 3 meters per hour. You see that in the red box, at 3 meters per hour filtration velocity instead of the originally designed flow velocity of 8 meters per hour. So if they would go to 8 meters with their sand filters, the SDI would go to endless 6.6 and higher, and they would have a quick fouling of the RO membranes. So we tested here our filter media. We achieved an SDI of 1.3 at 8 meters per hour. This was consistently proved over a longer period of operation, as you can see here on the right side on that graph. This plant is going to install the media first in a larger full-size installation in the horizontal filters you see here on the screen until the plant will be retrofitted with the correct pipe diameters, because there need to also be done some adjustments on the hydraulics and pipe diameter on the plant, which were also not fully in line with the flow rate required. So here we go up. We tested it up to 320 cubic meters per hour. That's the filtration capacity on that filter, and we run it between 8 to 11 meters per hour filtration velocity. Another project in Morocco, 5,000 cubic meter per day, recently installed, where we also run in front of a seawater RO plant. We are using 14 vertical filters at around 12 meters per hour filtration velocity. Important to mention is we can actually run our media up to 20, even 25 meters per hour filtration will give you a huge savings on surface area and capex for your filters. Yeah. Here another one is a big, large desal plant expansion in Spain. So they had already running the plant. We made a testing with Aquamed in Spain, And we could prove we could run at much higher filtration velocity at consistent SDI. So they decided to go for the expansion with our filter media. And actually, that's what I said before, is they had the ROI was almost on day one, because they saved half of their horizontal filters, which comes at even more cost than our filter media, which is more expensive than sand. We can run it at the same filtration performance, but at higher filtration velocities compared to the sand filters in place. Yeah. So these are 4,200 cubic meters per hour at 50 meters per hour filtration velocity, 6 large horizontal filters. Then another project we did in Greece, achieves 1,100 cubic meters per hour through vertical and horizontal filters for the largest refinery in Greece. Here we achieved SDIs much less than 3 and turbidity reduced to less than 0.5 NTU from around 10 NTUs. Here we also had issues, or the customer has issues with hydrocarbon and oil, because he uses the seawater for cooling processes, and sometimes these cooling heat exchangers have leaking oil. Sometimes they get up to 5 ppm of oil. We have quite a good oil removal with our filter media, over 90%, that we can also remove the oil, and which are quite good also removed during the backwash then after that. So other projects like we did, like smaller project for RO pretreatment in pharmaceutical plants, where we had issues sometimes with iron manganese removal. So we also have a very good iron manganese removal, as I mentioned to you before, with our AFM standard, which is negative charge. So we have fine iron manganese particle removal performance, which is quite important in some applications where your iron manganese is higher. In this case, they also had the Pseudomonas problem in the sand filters. This was eliminated from day one because of the reduced biofouling in the sand filter. We also do tertiary effluent treatment for reuse of water from municipal wastewater plants. So this was actually my final slide. There's a lot of benefits. It improves our membrane system and operation performance. Biofouling is dramatically reduced. The membrane lifetime increased because you have reduced cleaning cycles, and then of course many other life cycle cost benefits, which helps you in the operation of your plant. Thank you for listening. And if there's any questions, I can answer one or two of them.
Thank you, Johan. We have a question. Is the AFM currently being considered for drinking water process approval in the US? It's a question from Anna. Is AFM being considered for wastewater treatment approval in the US?
Okay. We already have NSF 61, so we can use it in any place where NSF 61 is approved. I think in most US states, 61 has been approved. We work on one of the larger desal plants in the US, which they consider to change from sand to our filter media. We needed the approval before we test. For wastewater, I'm not quite sure what you mean with wastewater approval in the US. Title 22 is something for membranes, but this doesn't exist for media filters as such, yeah? So it a little bit depends where are you going to use the filter media in a wastewater application or wastewater reuse application.
Do you use an inline analyzer for microbiological water quality to ensure the integrity of the media or show the performance of your media to remove bacteria?
So there is, it's a good question. So there are online analyzers for particle counts. So we strongly actually recommend to use these instead of turbidity or SDI, because they're much more directly measuring what is your performance of your filter, because SDI can actually be misleading. But otherwise, for bacteria, there is no online measurement. Typically, we see that purely by improvement of the biofouling behavior of your downstream cartridge filter RO membrane systems. Yeah? Or overall, if it's a new system, there is no biofouling or much reduced, if at all.
Last question I'm going to take is on the benefits of using FM for groundwater. You know, in Africa, we have a lot of challenges on groundwater. Does it help to increase the recovery or reduce the turbidity further with groundwater?
Yes. One of our most used applications in Africa is borehole water, very often containing iron and manganese, sometimes even fulvic acids. These can be precipitated before infiltration. We have a good performance in reducing the turbidity to very low levels. So here we have, that's quite a frequent application we have in Africa, is these typical borehole applications there with maybe humic fulvic and iron manganese content.
So we still have a couple of questions in the comments section, but I think we're running out of time, so we'll have to move to the next speaker. Thank you very much, Johan, for sharing all these insights. The presentation will be broadcasted later, so people can also watch it online and reach out in case they need anything.
Thank you very much, everybody, for listening.
Take care. So our next speaker is joining us from AWC. Beatrice, I think it's early for you in the morning. We've got very good attendance from all around the world, from Australia, Philippines, to the US and Latin America.
Thanks everyone for joining.
Thank you. The floor is yours. I'm going to leave you directly with the presentation.
Hi, everyone. Thank you so much for being here. Today, we'll be talking about how we're going to squeeze every last drop, essentially ways we can enhance system efficiency or RO performance. Before we dive in, I actually want to talk about why this is so important and relevant, specifically nowadays. There's a large push to conserve water, reduce energy consumption, and build more sustainable water treatment systems. There's more than just one way to be efficient. We often think about increasing recovery, which is certainly true. There's a lot of different parameters you want to look at. You want to look at chemical consumption, energy consumption, downtime, the amount of time we're cleaning, operational costs, but also environmental impact. The question becomes, if these are the goals that we're designing for, how come systems often don't perform in this way? They're not usually performing at the efficiency level that they're designed for. In practice, they usually fall short of that. The reason typically is related to fouling, more often than not. Essentially, it's the reason why systems are going to underperform. It can build up quietly, and by the time it gets caught or addressed, the system might have been running under the level that would be appropriate for the efficiency of the system, right? Before addressing it, it's important to talk about diagnosing it. Before treating the symptoms, I recommend understanding and diagnosing the issue. Let's talk about the fouling types. There's a few different ones. We're going to focus on the most common ones, but scaling, organic and biological fouling, suspended solids, chemical fouling even could be a type of fouling that we run into. And they're not a one size fits all. They're going to be unique and they can behave differently, show different symptoms, and require a different approach to clean or prevent. So understanding what is fouling your system is the key to selecting the right solution. So let's talk about scaling. This one's pretty common. I'm sure everyone's run into this issue before. It usually will occur in the tail element or the last stage of the system towards the very end. And that's because that's where the concentration of the water is the highest, right? As we're starting to concentrate that water, we have things coming out of solution because they reach saturation limits. And these scales can reduce permeability, so basically require more pressure to produce the same amount of water, increase differential pressure. Oftentimes it leads to irreversible damage. And the reason why, you can look at some of these images. I'm using some examples here. Take a look at calcium sulfate. These crystals are extremely sharp. So once they form on the membrane, even if you can remove it with cleaners, the problem is now there are going to be holes on the membrane that are uncovered. This means you're going to have worse permeate water quality. So maybe you'll have to replace those membranes more often. The best way to prevent scale is through proper pretreatment. The most common way is through anti-scalant. The one thing to keep in mind is I'm showing you guys a variety of different types of scales, and different types of scales will require different ways to treat them. And usually the anti-scalant has to be selected for the specific water quality. So just keep that in mind. And oftentimes you can actually have a combination of a few things. In the example I'm showing here with silica, you also see a little calcium carbonate crystal. So it depends on a variety of factors. But we also have biofouling, and this one is the most common type of fouling. Everyone suffers it to some extent, some more than others. It's essentially just caused by bacteria that's entering the system and then forming a very sticky, slimy film. The film can restrict the water passage through the membrane. It can actually change the salt rejection as well because it's creating a barrier on top of the membrane. It can, if allowed to grow, raise the differential pressure, increase feed pressure, so lowering the permeability of the membrane. Sometimes if you have cartridge filters ahead of the RO, that might be also getting impacted. The replacement frequency is also extended or increased. A common issue with biofouling is the fact that your CIP frequency usually starts getting shorter and shorter over time if it's not addressed properly. Pretreatment is a really good way to address it. The problem is sometimes pretreatment could be the issue. If we think about a lot of sites doing chlorination, we need to quench that chlorine residual before it enters the RO, and plants will dose sodium bisulfite or SBS. The issue is it can be overdosed if not monitored carefully. And then this, if it's overdosed, it's basically nutrient for the biofilm, and it can lead to really dense, hard to remove biofilm. You can see here on the images on the right, they're from a membrane that was doing exactly that. In those cases, just using commodity cleaners or standard high pH won't be enough. It's really tough to remove. You need to take all of this into account to address it properly. Now, often you'll see this on the first stage because it's entering the system as is. And then we have suspended solids. These are common in all types of systems to some extent as well. In the membranes I'm showing here on the images, it's pyrite, so iron disulfide. It's coming in from their wells. They had a well collapse and these particles came in, passed through the cartridge filters and fouled all of their membranes. You can't even see membrane surface, whether it's on the actual image itself of the membrane or the SEM EDS of the membrane coupon. Usually these are going to be really small particles, and they're usually going to deposit in the first part of the system, so the first stage before. But sometimes it can be fine enough that they go through and end up collecting towards the end of the system. And the way we typically address this in the pretreatment through physical filtration, for example, Jochen talked about having tighter cartridge filters, but sometimes the replacement might be a lot, so that's inefficient as well, or having glass media or some sort of sand strainer or MMF. There is a way to address it. You just need to understand the size of the fouling or the suspended solid. So now we've looked at the different types of fouling. I want to focus a lot on the consequences of what each of them can mean to your system. The first one would be DP, or differential pressure. When we think about the feed spacers of the membranes, they're channels for the water to flow through. And that's what I'm trying to show here with this green cylinder. Essentially, as we have fouling build up and start growing thicker on these channels, we're making the path of water smaller. So the friction is higher, the differential pressure, the pressure loss is higher as well. That can be really damaging for the membrane, also inefficient, like what we're talking about here. Reduced permeability is another impact that the fouling can have on your system. And I'm showing here a membrane that's severely biofouled. And if you think about all of this solid covering the membrane surface, making more pressure to be required to push the same amount of water through that membrane, it's extremely inefficient, needs to be addressed. And then more frequent cleanings. I'll touch on this briefly now, but we'll talk about this more extensively down the line. But essentially, we want to make sure that the cleaning is done correctly. And if they're not, what ends up happening is, let's say we stop this cleaning at hour 2 or 3, for example. Not all of the fouling was removed. It's not going to take half as long for the fouling to build up enough to the point where you have to clean again. So it is important to address the fouling before it forms, but also afterwards, so that the cleaning frequency doesn't have to be more than it needs to be. The other impact, and this is a really big one, is membrane lifespan. So when we talk about these solids collecting on the membrane, I mentioned before the salt passage issues that it can have, right? So I'm going to zoom in here. This is a dye test. When we autopsy a membrane after the cleaning, we do a test with a dye that's a molecule large enough that it should not be passing through the membrane. But when there's physical holes, right, abrasion on the membrane, you can actually see the dye pass through to the permeate side. And that's exactly what you're seeing right here. And this is being caused by scale that forms on the feed channels or contact points of the feed spacers. Eventually, your permeate water quality will reduce, and you might have to replace your membranes much earlier than expected. This damage can actually be a lot more severe than you would think. Right here, I'm showing you an example of a plant that suffered from severe biofouling, and they had a very high differential pressure for a long time. And what the differential pressure really means is pressure loss, but the membrane's absorbing that pressure. Eventually, after running it at a high DP for a long enough period of time, the feed spacers started being pushed through the membrane. The problem here is, even if you were to clean this membrane and remove all of the biofilm, now it's not a membrane you can really use, because what kind of permeate will it produce? So it's important to prevent early to not have to shorten your membrane's lifespan. The overall issue here is we're reducing recovery or stability of the system, and more importantly, reliability in your system too, because you can't rely on it to run efficiently and actively all the time. One comment I do want to make here is about recovery, because there is a big push across the industry to increase recovery, maximize as much of the water recovery you can have and minimize that waste of the reject stream. The problem is, every time you're pushing the system harder, you're also pushing the chemistry to its limits. So as we concentrate the water more, we have more things reaching the saturation limits or even going beyond, and the scaling risks increase. For most common scales, that might not necessarily be a problem. There are plenty of anti-scalants out there that can handle, let's say, really high concentrations of calcium carbonate. But for something like silica, historically, it's been a limiting factor for recovery for a majority of systems. And usually these systems are capped at around 200 ppm silica. Sometimes you'll see them maybe trying to go push to 300 ppm in the reject. But today there are products like silica dispersants that can go much higher. So PureFlux SI is an example of products we've been testing that can reach beyond the threshold that was previously assumed to be the maximum. The point here is if silica is holding you back, it's worth reevaluating what's possible. There's always technology beyond just the membranes themselves. The whole system, when recovery drops or chemical use skyrockets or pumps have to work harder, driving up energy bills, or CAPs are becoming more frequent, labor increases, and eventually you're looking at early membrane replacement. So OPEX, CAPEX are all going up, definitely having a less efficient system, less sustainable, with a much larger impact to the environment. The first and most important one is to stop it before it starts. This is where the pretreatment is going to come in. It will depend on what we're trying to address. If we're talking about suspended solids, physical pretreatment would be important. But for scales, something as simple as an anti-scale would be enough. I'm just going to show you guys a really good example. It's easy to visualize. Both of these images side by side are from a tail element, the second stage, last element of that stage from a pilot system. And that pilot ran for about a year. And this is what you'll see on the image to the left. That membrane ran with anti-scaling in the pretreatment normally for about a year. We autopsied it towards the end. You can see that there's a little bit of organics that built up, so biofilm, a little bit of iron, but overall not bad for a year without a single CAP being performed. After that membrane was spooled, the new tail was put in and they wanted to run a trial with no anti-scaling just to see how long the system would last before shutting down. In less than 48 hours, the system shut down. We pulled that element for another autopsy and you can see the big difference, right? So in less than 48 hours, the membrane got completely covered in calcium carbonate and iron. This is just showing why we do, for example, anti-scaling in the pretreatment. Some plants will also do acid. It's important to do this because mitigating or preventing it from happening in the first place is much better and cheaper than trying to address everything afterwards. So even with good pretreatment, cleanings are still going to be a part of the system maintenance. How you clean is also really important. You want to have good pretreatment so you don't have to clean excessively. But once you do have to clean, things will still form within the system as it runs. You want to make sure you're doing it with a purpose, understanding what needs to be done for that system. Not all phthalates will respond the same to the same chemistry. Sometimes you might need a different protocol depending on what you're trying to clean. So in this case, I'm just showing an example. Iron fouling, it's usually really common. Right here, you'd want to use a low pH cleaner. We use C217, and I'm showing before and after images that was an effective cleaning. But let's say this was biofilm. I certainly would not want to use the same chemical here. Biofouling, usually we want to clean at a high pH, and depending on how severe, this is that same plant I mentioned to you guys earlier, was overdosing SBS. And we actually had to do a cleaning study with 2 cleaners. They were both top performers, specifically for biofouling, like biological removal. One was completely ineffective, and we wouldn't have known unless we tested the protocol. It was the exact same protocol as the other one. This shows you how not everything is as straightforward as it might seem. For a lot of severe biofouling, maybe cleaner A would have been a perfect solution, but not for this type. We want to always make sure we're doing the correct chemistry for that system and that water quality and that foulant. And then the other important thing is don't just clean because you have it on a schedule. Excessively cleaning when it's not needed can also compromise membrane integrity, but also efficiency, chemical waste when it's not necessary. But you certainly also don't want to wait. It's a balancing act, and usually you want to do it data-driven. I'll talk about that in a second. But let's talk about also the protocol. Time is a big factor when it comes to cleaning. So how do you know when to stop cleaning? The right answer here is when the foulant is completely removed. But that can be a little bit hard to know, especially when it's the first few cleanings. Usually I recommend that you do a cleaning study before you try to clean a new system. It's the best way to understand what chemical to use, how long you should use it. The protocol is just as important as the chemical selection. Here, I'm also showing a little bit about the different cleaners. This is an organic foulant that was being removed in a visualization study. So you can see here that caustic was used, pH of 12.5, 45 degrees Celsius. So it's a really extremely aggressive condition, right? And here we have the exact same foulant being removed with the high pH C227 cleaner. So it's for organics, biological removal. And at a much lower temperature, it actually was able to fully clean the foulant in less time. The first cleaner didn't even remove it after the 6 hours, but this one was after 2 to 3, it was fully removed. So it's important to talk about the protocol, but also, like I said, understanding what will work for that foulant. Now I want to ask you to reflect a little bit. If you're operating an RO system, are your CAPs working? Are they effective? How do you know that? Hopefully the answer here is talking about normalized data. The golden standard when you're looking at a CAP performance is pre and post normalized data performance. Cleaning more doesn't mean that you're cleaning better, right? This is a system that was struggling with silica scaling. This is the second stage permeability. If you are suffering with silica scaling, pay attention to normalized data, because a lot of systems will look at differential pressure, sometimes even rod differential pressure, and that's not a good way to look at it, because silica won't show up on the DP for a long time until it grows thick enough to start blocking that feed spacer. So it's just a tip I want to throw out there if you are having a system with a high silica scaling potential. But you can see here that the permeability of that element over a few years started dropping to almost 0 gallons per minute. They started cleaning with cleaners that weren't effectively removing it. So you can see with the red lines, they're marking the amount of times they try to clean, and the recovery really was not very large. You see a small jump in the permeability, but you expect it to go back up to where it was in the beginning, just that tiny little step change. Then in green was the cleaning they did after they were able to do an autopsy, understand what the cleaners that were required in the protocol and the concentration. In the lab, it showed that it would have restored performance. They did it on site, performance was restored as expected. So the goal here, the message I want to share with you guys is that it's important to clean intelligently, not just frequently. And that's the goal for being efficient. But we finally come to the monitoring side of things. So one of the most underused and powerful tools in system performance is normalizing your data. So this can help us detect any change in the performance before it's too late, before any damage takes place, or it's much harder to clean. It helps you establish when to clean. Usually, for example, normalized permeate flow would be about a 15% loss. So you wouldn't necessarily want to clean it before that, but you also wouldn't want to wait until it's past that, because beyond that, you start having issues where the membrane can get damaged, or now the foulant will be too hard to remove. It's also really useful for troubleshooting. If something changes suddenly and you have the data normalized, you can kind of understand more of what happened. What steps should you take? Should I do an autopsy? Is this a scaling concern or biofouling normalization? But essentially what normalization is doing is just standardizing it. So for example, temperature will have an impact on differential pressure. So water, the viscosity changes as the temperature change. In, let's say, during colder seasons, if you're treating surface water, the water will be colder. So that means that it's more viscous. The DP would be higher by default. If you saw your DP going up during winter, it's not necessarily a sign that your membranes are fouling. It's just a sign that the water is more viscous. When you normalize, it's accounting for all of these parameters that are changing that don't necessarily indicate a change in the performance of the system itself. Normalizing is very important. The other side of the equation is monitoring. Make sure that you're looking at these trends, interpreting them, and then act when the time comes. I'm bringing back this example I showed in the beginning. This was a plant that was struggling with scale in the second stage, and they would clean. You see that the performance would restore. So the cleanings were actually working really well, but the performance would drop so fast. It didn't make sense for the kind of water they were treating. The system was really inefficient for a long time. And by looking at the data, understanding the issue, doing an autopsy, understanding what the scale that was building up was, and addressing the pretreatment, which would be the anti-scalant, they were able to do that final cleaning. The performance is, plateaued, so stabilized. And this happened a few months ago. It's still ongoing, but the performance hasn't changed since then. This was a really simple way that normalized data helped the system understand what was holding back their efficiency. And it was a simple fix. So if there's one thing to take away from today is this: you can't achieve high efficiency without controlling fouling. Pretreatment is going to be your first line of defense. CIPs are going to be your response. Monitoring is how you guide both and make sure that they're working, right? When these all work together, you get recovery, reliability, sustainability, and efficiency. Now, I will open it up for any questions you might have, and I'm happy to dive deeper into anything we discuss and let me know.
Thank you so much for this great presentation. We do have a few questions and I'm going to share them. What is the best antiscalant in water with high concentration of calcium sulfate? Is there any quick test method for fouling type identification?
So to answer the question, it depends. The antiscalant, the best way to really recommend, because maybe there's a high concentration of calcium sulfate, but there might be other things in the water that interfere as well and need to be taken into account. The best way to go about this is to run a projection with the complete water quality. And for example, Proton, which is our software, it will take everything into account and essentially recommend the antiscalant for that water quality. If you suspect there's scale in the system and you get a sample, you can do an acid drop test where you drop a little bit of acid on it and see if it effervescens. So bubbles up is the thing you're looking for. If it does, you know that it has carbonate in it. So it's an indication that you might have, let's say, calcium carbonate scale. If it doesn't, then maybe you're looking at calcium sulfate, for example, or silica, because it's hard to distinguish it with your eyes. When it's biofouling, you can usually see that it's slimy or it will have an odor to it. The message is not that you can identify with your eyes. You should still have it checked, but because it's not very easy to distinguish, but there's a few tests you can just look at it and try and identify, group it.
And between fouling and scale formation, which has a greater impact on the differential pressure?
It depends, because if we're talking about biofouling, as opposed to any other type of fouling, that usually has a really big impact on the differential pressure. But scale, specifically calcium scales, so calcium carbonate or calcium sulfate, those usually have a huge impact on DP very fast. So it really just depends.
Okay, great. I think we've got an excellent session. Thank you for leading this. Combined with the presentation of Jochen, it was a good end-to-end discussion. Thank you a lot for joining us, and thanks for everyone who has joined. We're going to record the video. It's already recorded, and we're going to be posting it on our social media channels. So thank you, everyone, and thanks for our speakers.
Thanks, everyone.